Hi, everybody. So in this last section of our discussion about factor groups and normal subgroups, I want to talk about the idea of a simple group. A simple group is a group which has no non-trivial normal subgroups. And these are, in some sense, the building blocks of group theory. And I'll give a little bit of a feel for why that's true in this discussion. So just to restate the definition, a group G is simple if its only normal subgroups are the trivial group and the entire group G. And as we'll see, the groups Z mod P, where P is a prime, are simple. And as we're going to show in a moment, the only abelian non-trivial simple groups are the groups ZP, where P is prime. So Z2, Z3, Z5, Z7, and so forth are the only non-trivial abelian simple groups. So let's look at this, let's prove this, and in the process we'll get a little bit of a feel for what's special about simple groups. So let's remember that in an abelian group, every subgroup is normal, because the condition that GHG inverse equals H is automatic, since GHG inverse is GG inverse H is H, using the abelian property. So if you're simple and abelian, then the only subgroups of G are 0. Only subgroups, not just normal subgroups, are 0 and G. So suppose G is non-trivial, and choose X in G, and consider the cyclic subgroup generated by X. Well, if G is simple, then it must be the case that H is equal to G, because this is a subgroup, and the only subgroups G has are the trivial group, and H isn't trivial because it contains X, or the whole group. And this tells you that G is cyclic, because it's generated by a single element, by the powers of a single element X. And we know what the cyclic groups are. So either, first of all, H is Z, but Z is not simple. It has subgroups. For instance, 3Z is a subgroup of Z. So since Z has subgroups, we can cross this off. Z is not simple. The other cyclic groups are G equals Z mod N for some N. Well, if N is not prime, then choose a divisor which is bigger than 1 and smaller than N. That's what it means to not be prime. It means that you have a proper divisor. And consider the cyclic group generated by D. So this is actually a proper subgroup. We know how many elements does it have. It has N over D elements. So it's not all of Zn, and so Zn isn't simple. But if G is Zp, then X is a subgroup of G, but the order of X has to equal P. It's got to be a divisor of the prime, and the only possible divisor of the prime is P itself. And so therefore, the cyclic subgroup generated by X has to be equal to all of G. And that means that any subgroup of G is the whole group. And so G is simple. So by this process of elimination, we've shown that if you're abelian and simple, you have to be cyclic. And if you're cyclic and simple, you have to be finite. And if you're finite and cyclic and simple, you have to be ZP where P is a prime. And in that case, you are actually a simple group. Well, what about more complicated simple groups? Well, it's a theorem that if you take, remember what the alternating group is. The alternating group is the subgroup of the symmetric group consisting of even permutations. And it turns out that the simple group with on n elements is alternating once you get past n equal to 5. So just to remind you, what about if n is less than 5? So the alternating group on 3 elements is just the group of 3 cycles, because it's the even permutations in the symmetric group with 3 elements, and there are transpositions and 3 cycles, and only the 3 cycles are even. So A3 just consists of the identity element and the 3 cycles 1, 2, 3, and 1, 3, 2 inside S3. And that's a cyclic group with 3 elements, so it is simple and abelian. What about A4? Well, A4 contains the subgroup consisting of the products of 2 permutations. If you this set is closed. If you multiply any 2 of these, you get the third. And so this is a subgroup of A4. How do you know that it's a normal subgroup of A4? Well, if you take, you use the fact that if you have any permutation, so take any G which is in A4, and think about G 1, 2, 3, 4, G inverse. Well, since G is in A4, G is also in S4, because A4 is contained in S4. And we had a homework problem which shows that if you conjugate a permutation, you get another permutation with the same cycle structure. Namely, it's a product of two disjoint transpositions. But in A4, these are all of the products of disjoint transpositions, because to make a disjoint transposition in A4, you pick 2 elements, and there are how many? 4 choose 2. There are 6 ways to do that. And having picked 2 elements, the other 2 are determined. But so that would seem like you would have 6 products of permutations. But if you reverse the order, you would get the same one because they commute. So there are only 3 products of disjoint permutations in A4. So if you do G times, let's call this subgroup H. If you do G, H, G inverse, you have to get H because G, E, G inverse is E, and G times A, B, C, D is another, G inverse is another product of transposition, of disjoint transpositions. So it's not only true that this is a normal subgroup of A4, but it's a normal subgroup of S4, because when you conjugate, you don't, actually, we should, to be normal in A4, you have to show just that if you conjugate by even permutations. But in fact, if you conjugate by any permutation, this is a subgroup. So A4 is not a simple group. It is a theorem that A5 and actually AN is simple for n bigger than or equal to 5. And there is a proof in the text. And what you'll see in that proof is that this is a little bit complicated and it's a long calculation. Essentially, what you would do is you assume that H is a normal subgroup of A5, and then you show that H has to contain 3 cycles and that the 3 cycles generate A5. So you basically use the fact that 3 cycles generate A5. And you force the 3 cycles into H using conjugation. Because since it's normal, if you have one thing in there, then all the conjugates of that thing have to be in there. And that gets you A5, and then to do AN, you basically have to do the same argument, but you have to be even more careful. So in some sense, it's an inductive argument to get AN for all n bigger than or equal to 5. I'm not going to work through this proof because it's kind of complicated and not particularly illuminating. I will, on the web page, give some links to some resources on the web for if you want to look at other proofs besides the one that's in the text to get a sense for how this works. But let me briefly wrap up this discussion of simple groups by saying why we might care about simple groups. And the idea is that there's a general problem, which is classify groups. So, I mean, for example, we know there's only one group of order 2 and there's 2 groups of order 4, and there are, it's only one group of order 3, and there's only one group of order 5, and there's 2 groups of order 6, and so on. And one way to classify all groups is you need some way to simplify the problem. So you're given a, let's say now you're going to make this easier, you're just going to classify all finite groups. So you start with a big finite group, and you want to say, what can you say about it? Well, if H is a normal subgroup of G, then you can look at H and G mod H. And in some sense, G is kind of like built up out of these 2 parts. It's not necessarily just the product. In fact, it's not going to be the product in general, but at least it's built up out of these 2 smaller groups. These are both smaller. So if you have a group with a normal subgroup, you can understand it by looking at the normal subgroup and the quotient group. But if G is simple, then there's nothing you can do. And you have to understand it as it is. And that's the sense in which the simple groups are the building blocks of all groups. So if you want to understand groups of order less than 60, well, the only simple groups, it turns out, of order less than 60 are the cyclic groups with prime power order. The first place you run into trouble is with A5, and that has order 60. So you can use this idea of reduction and somehow try to explain your groups in terms of cyclic groups. But once you hit A5, you're in trouble. And then there turn out to be a collection of infinite families of cyclic groups, and then a few bizarre, exotic examples of cyclic groups, of simple groups, which you need to understand by other methods. And so for people working in finite group theory, the simple groups are both the most difficult groups to understand, but also in some ways the most important ones to understand.